Welcome, nocturnal minds, aboard. Your learning journey starts now. So, having explored the essence of natural laws in the naturalistic approach, we now turn our attention to a fundamental question that has long captivated philosophers. What is real? Specifically, when it comes to science, do we believe in the things it tells us about, especially the ones we can't see? This brings us straight into the heart of the realism versus anti-realism debate. It's not just about atoms or quarks. It starts with the seemingly simple stuff around us. Alright, so what exactly are we arguing about here? Think of it like this. Realism has two main flavors. First, there's the existence dimension. This is pretty straightforward. Do we believe these things actually exist? For everyday stuff, like rocks and trees, most of us say yes, obviously. For science, it's about whether things like electrons or gravity are real. Now, the second dimension is independence. This is where it gets tricky. Do these things exist on their own, separate from our minds, thoughts, and perceptions? Or are they somehow tied to our minds? Idealists, historically, often said, okay, they exist, but only as ideas in our heads. More recently, thinkers heavily influenced by Kant, like Thomas Kuhn, pushed further. Maybe the world itself depends on our concepts, our ways of thinking. We don't just discover the world, we construct it, sometimes even building different worlds based on different concepts. Realists, though, draw a hard line. Nope, the world is out there, independent of us, whether we like it or not. The big battleground is usually this independence claim. Now you might think, why fuss over existence? Isn't the real question about whether things are mind independent? Well, existence is crucial. It tells us what we're even talking about. If someone says, I'm a realist, but doesn't commit to anything existing, well, that's not very helpful. It helps distinguish a serious position from just saying something exists out there. And critically, especially when we get to scientific realism, the main fight isn't always about whether unobservables exist, but often about whether they exist independently of our theories or concepts. So existence sets the stage, but independence is often the main act. Let's nail down common sense realism first. This is the bedrock, the idea that the stuff we see, touch, hear, smell, and taste, the physical world around us, exists independently of our minds. It's not just a fleeting dream, nor is it just a collection of mental images. It's out there, and guess what? Almost everyone outside philosophy departments just assumes this is true. It's common sense, so the big puzzle is, why do so many sharp philosophers find this compelling idea so problematic? What makes them doubt the very ground beneath our feet? The classic culprit is extreme skepticism, famously kicked off by Descartes. He basically said, hold on, how do I know this isn't all a dream? Or maybe an evil demon is messing with my senses? If you can even entertain that possibility, how can you rationally believe in a solid, independent world? It opens a huge gap between your mind and the supposed external reality. Idealists say, don't try to bridge that gap, just ditch the idea of an independent world. Let's say the world is made of ideas, or that we construct it. Fast forward to more recent times, and you get a semantic twist. Instead of focusing on epistemology, can we know? Some argue about semantics, can we refer to? They say, we can't possibly point to or talk about that independent realist world in a meaningful way. Therefore, whatever we refer to must be something we create or make. It's like saying, if you can't name it properly, it doesn't exist. Okay, so abandoning realism for idealism sounds like a solution to the skeptical problem, but it comes with a hefty price tag. Imagine constructivism, the idea that we literally make the world by imposing our concepts. How do we make dinosaurs, or stars? It sounds a bit like magic, doesn't it? Many find it bizarre, so what else can we do? One approach, often called the Moorean response, basically says, hang on, these skeptical arguments are based on weird hypotheticals. Common sense realism feels much more solid. Maybe we should start with realism and show why those skeptical worries are overblown. Think of it as putting metaphysics first. Then there's the naturalist angle. From a naturalistic viewpoint, these anti-realist arguments often feel like they're floating in the air, No empirical evidence, just philosophical speculation. Realism, on the other hand, is grounded in our experience. So, the naturalist says, you guys are using the wrong tools, looking in the wrong direction. Now, let's circle back to that evil demon worry. It highlights a deeper issue, weak underdetermination. Basically, any set of observations you make could in principle be explained by multiple different theories, including crazy ones like the evil demon hypothesis. Your observation that the coffee is hot doesn't logically entail that coffee exists, nor does it rule out the demon scenario. This means we can't just deduce theories from observations. To get past this skeptical hurdle, we need some kind of ampliative reasoning, jumping to conclusions that go beyond the strict logic of the evidence. This is how we justify common-sense realism. And here's the kicker for scientific realism. The whole debate about unobservables only really kicks in after we've already accepted that we can somehow know the observable world. So, scientific realism isn't fighting the same battle as extreme skepticism. It's a new challenge built on top of that foundation. So, how do we defend belief in the unobservables? The heavyweight champion of arguments for scientific realism is the success argument popularized by Hilary Putnam. It's beautifully simple. Science works. Its theories make predictions, and remarkably often, those predictions come true. Why? The realist says, because the theories are mostly right. The theoretical terms like electron actually refer to something real, and the theories capture the world approximately. Think about it. Why do we observe things behaving exactly as if atoms exist? The most plausible answer is that atoms do exist. Sometimes, the argument gets even stronger, invoking miracles. Wouldn't it be a miracle if all these complex theories were so successful if they were just empty mathematical constructs with no connection to reality? Realism, then, offers the only good explanation for this sustained success. But wait, there's a counter-argument famously laid out by Larry Lawton. He points to historical examples like phlogiston theory, which was wildly successful in explaining combustion before being discarded. Phlogiston, realism struggles here. How do you respond? Well, the realist can push back. Maybe phlogiston wasn't truly successful by today's standards. Maybe it wasn't a well-established theory in the sense realism demands. Or maybe it didn't posit essential unobservables. But even if some theories on Lawton's list survive scrutiny, the realist can still point to countless other theories where the success argument holds perfectly fine. A clever twist is to say that even if a past theory like phlogiston was false, its success might be explained by the unobservables of the theory that replaced it, like oxygen. But can anti-realists offer a better explanation for success? Van Frassen tried a Darwinian analogy. Successful theories survive because they're fit, like in evolution. But that explains why we keep them, not why they work. Arthur Fine and Jarrett Leplin proposed surrealism. Maybe the world's underlying structure just happens to produce experiences that match what successful theories predict, even if the theories are wrong. Leplin argues this surrealism doesn't quite cut it as a rival explanation. A key point often raised against the success argument is its reliance on inference to the best explanation or abduction. Think of it as choosing the simplest or most elegant explanation for why things happen. But some anti-realists, like Van Frassen, are wary of abduction. So, can the realist use it? Boyd makes a powerful case. Scientists constantly use abduction to draw conclusions about observable things. Think about diagnosing an illness based on symptoms, or inferring a hidden object from its effects. If anti-realists accept that we can know observable things through abduction, they have a problem. Boyd's strategy is brilliant. Expose the anti-realists' epistemology for observables, show how it relies on some form of ampliative reasoning, and then argue that the same reasoning applies to unobservables. It's like saying, you can't deny the method for the visible world, so you can't deny it for the invisible either. If the anti-realist can't justify their knowledge of the observable world without something like abduction, then the realist's use of abduction for unobservables looks perfectly reasonable. And honestly, justifying any ampliative method seems equally challenging, doesn't it? Beyond the Ming success argument, there are other related explanationist lines. Boyd, for instance, asks, why is our scientific methodology so darn reliable? It consistently leads to theories that make accurate predictions. The realist answer, because the methodology itself is shaped by our theories, and those theories are largely true. Anti-realists who reject the truth of theories struggle to explain why this particular methodology works so well. Another angle from David himself is quite basic. Believing in the unobservables allows us to make sense of the observable world in ways we couldn't otherwise. Think about explaining chemical reactions by appealing to atoms and molecules. Without believing in atoms, you're stuck with vague notions of affinity. Believing in the unobservables gives us explanatory power for the observable. Okay, enough defending realism. Let's look at the counterarguments. The big one is the underdetermination argument. This starts with a seemingly innocuous premise: empirical equivalence, e.e. Any scientific theory that makes claims about unobservables will always have alternative theories that make the exact same observational predictions. Think of two theories, T and T prime, that both predict the same experimental results, but differ on what unobservables are involved. The argument then jumps to a stronger claim: strong underdetermination. Not just potentially equivalent rivals, but rivals that are equally supported by all possible future evidence. If that's true, then what difference does it make what a theory says about the unobservables? Ampliative reasoning can't distinguish between them. So, committing to the unobservable parts of a theory seems like unjustified metaphysics. Even if you've escaped the evil demon, realism about unobservables looks shaky. So, how strong is this underdetermination argument? Well, constructing empirically equivalent rivals is easy. Take any theory, T, strip away its unobservable claims, and add the negation of T. Boom, you have a rival T-star that predicts the same observations. But are these contrived rivals genuine competitors? Realists say, nope, our existing methods for dealing with skepticism, the very methods that let us accept common-sense realism, allow us to dismiss these artificial T-stars. For the underdetermination argument to really threaten realism, it needs a much stronger version of equivalence. Let's call it EE-san. Rivals that remain indistinguishable even when combined with any conceivable future auxiliary hypotheses, new instruments, background assumptions, etc. But here's the rub highlighted by Lawton and Leplin: we have no reason to believe EE-san. Science progresses, we invent new tools, new theories emerge. What seems equivalent today might not be tomorrow. Given our endless capacity to generate new ways of testing theories, absolute unbreakable empirical equivalence seems highly unlikely, perhaps impossible. Even a weaker version, EER relative to current auxiliaries, fails to sustain the conclusion and is probably false too. The underdetermination argument, therefore, collapses because its foundational premise is too weak. Another major blow against realism comes from the pessimistic meta-induction, again associated with Putnam and developed by Lawton. The argument is chillingly simple. Look at the history of science. All those grand theories of the past, phlogiston, caloric, luminiferous ether, they all posited fascinating unobservables, and guess what? They turned out to be wrong. So, the meta-induction concludes, probably the unobservables posited by our current best theories, like dark matter or string particles, are also going to turn out to be wrong. It's a historical trend extrapolated into the future, casting doubt on the very confidence scientific realism requires. It suggests that maybe we should be skeptical of unobservables, period. How do realists fight back against this gloomy historical forecast? First, they can challenge the premise. Was the history really that bad? While phlogiston is a clear failure, atoms posited centuries ago clearly do exist. Many past theories, while incorrect in detail, contained significant truths. The historical record is messy, not uniformly bleak. Second, they can attack the inference. Even if most past theories were wrong, does that mean most current theories are likely wrong? Mark Lange calls this the turnover fallacy. False theories tend to get replaced faster than true ones, so a high failure rate in the past doesn't necessarily imply a high failure rate now. The inference requires assuming that the historical failure rate applies to the present, which seems questionable. Finally, and perhaps most powerfully, realists point to scientific progress. We have vastly better tools, techniques, and understanding now, than in the past. We're getting better at probing the unobservable world. If anything, we should expect our success rate with unobservables to be improving, not declining. This makes the pessimistic meta-induction's conclusion much less convincing. Unless the anti-realist can show that progress has stalled dramatically, the argument loses its punch. So, wrapping up the realism section, the core debates are fundamentally about the nature of reality itself, metaphysics. Skepticism throws a wrench in the works, forcing us to rely on ampliative reasoning even for the observable world. Scientific realism then becomes a distinct question built upon that foundation. The arguments for realism, particularly the success argument, hold water if we allow abduction. The underdetermination argument falters because its core premise is too weak. The pessimistic meta-induction raises a challenge, but it's weakened by the fact that scientific progress suggests we're getting better at understanding the unobservable, not worse. Overall, while the debate is fierce, scientific realism seems to have a solid defense against its main critics. Now, let's shift gears and explore another fascinating, and perhaps more controversial theme, relativism about science. This is the idea that scientific knowledge isn't some objective universal mirror of reality, but is instead deeply shaped by our specific historical, cultural, and conceptual contexts. It's a form of epistemic relativism applied specifically to science. The core claim that science, despite its aspirations, can't achieve the objectivity and universality it claims. Scientific theories are only true or justified relative to their particular social and cultural backdrop. It's a pretty radical departure from the traditional view. Relativists often frame their position by rejecting what Maria Bagramian calls the objectivist conception of science. Think of OC as the standard picture, one real world, one correct description. OCE, laws that are universal and value-free. OCR, a single, uniquely correct scientific method. OC3, a clean separation between how a theory is discovered and how it's justified. Stable meanings for scientific terms. OC5, the belief that different scientific views will eventually converge into one truth. OC6, and knowledge that steadily accumulates over time. OC7. Relativists systematically deny these points. They argue that science is inevitably colored by our perspectives, that there's no neutral standpoint, and that the very idea of a single objective method or converging truth is illusory. What drives this rejection of the objectivist view? Two main motivations stand out. First, there's a deep-seated epistemological concern. We humans are embedded in our cultures and conceptual frameworks. Can we ever truly step outside of them to grasp reality as it is? If not, how can we claim science achieves universal objectivity? Plus, different cultures and historical periods have different standards of reasoning and what counts as rational. There seems to be no single ahistorical yardstick to judge them all. Second, there is often a political and economic dimension. Relativism can be a tool for critiquing the power structures within and surrounding science. Science isn't seen as a neutral beacon, but potentially as an instrument of repression, serving dominant groups, silencing dissenting voices, particularly those of women and non-Western peoples. It's a way to challenge the perceived authority of Western science. Much of the contemporary push for relativistic views comes from the sociology of science. Thinkers like Barry Barnes and David Bloor, with their strong program, argue that social factors, norms, values, interests are integral to how scientific knowledge is produced. Bruno Latour and Steve Woolgar, in their seminal Laboratory Life, took this further with social constructionism. Their radical claim, scientific facts aren't discovered out there. They are constructed through the messy interactive processes of laboratory work, negotiations, interpretations, even data manipulation. As Latour puts it, the appearance of an objective world is the consequence of scientific practice, not its cause. Goodman used the analogy of making constellations. We connect the dots, imposing patterns. Latour even famously argued bacteria were invented in labs. The implication: scientific knowledge is deeply contextual, contingent, and potentially driven by interests. Feminist epistemologists have also contributed significantly to relativistic thinking about science. They critique traditional epistemology and science for being androcentric, reflecting the male perspective as the default. Some radical feminists argue that the ideal of objectivity itself is a male invention, serving patriarchal interests. They reject the neat separation between discovery and justification, arguing that seemingly neutral virtues like objectivity and rationality are often used to marginalize women's experiences and knowledge. Evelyn Fox Keller emphasizes that science, like society, is subject to social forces. Lorraine Code pushes further, suggesting that knowledge is a construct produced within social practices, and evaluation must be contextual. This can lead to the idea of a feminine sphere of knowledge, distinct from the masculine scientific one. However, there's a risk here. If feminine knowledge is characterized as subjective or non-rational, it risks reinforcing stereotypes and creating a new kind of intellectual ghetto. Postmodernist thinkers, drawing inspiration from figures like Foucault, take relativism even further. They view the very tools of science, reason, logic, rationality, not as neutral instruments, but as mechanisms of power and control. Foucault argued that each historical era develops its own episteme, a distinct way of ordering knowledge and truth, tied to its political and economic structures. Renaissance emphasis on resemblance, classical focus on identity, modern obsession with reason and science, each generated its own version of truth. For Foucault, science, especially the social sciences, is deeply intertwined with power, used to manage and control populations. Rejecting dominant scientific norms then becomes an act of political resistance. This perspective fueled the intense science wars of the late 20th century, epitomized by the so-called hoax, highlighting the clash between postmodern relativism and the scientific establishment. Where does much of the philosophical fuel for relativism come from? A key source is the Duhem Quine thesis of underdetermination. Remember that? The idea that evidence never uniquely supports one theory. You can always find auxiliary hypotheses to save a failing theory. Quine even went further, suggesting any statement could be made compatible with any data if you tweak enough else. This opened the door for irrationalist and relativist readings. Lawton saw it as meaning no rational basis for theory choice when theories are observationally equivalent. Feyerabend used it to argue for democratic relativism. Different cultures can have equally valid worldviews, rejecting the idea of convergence. O.C. Liu. Pickering, within the sociology of science, argued that, because theory choice is underdetermined, scientists inevitably fill the gap with their judgments, which are inevitably influenced by social and historical factors, thereby undermining the idea of a single scientific method. O.C. Sun. Another cornerstone is Kuhn's concept of incommensurability, stemming from his analysis of scientific revolutions. Kuhn argued that science doesn't progress smoothly via induction or falsification, but through paradigm shifts. A paradigm is a whole framework, core theories, methods, assumptions. When a revolution happens, the old paradigm is replaced by a new one, often involving incompatible concepts and problem sets. Kuhn famously said, "Though the world does not change with the change of paradigm, the scientist afterward works in a different world." This idea resonates strongly with relativists. If scientists working under different paradigms literally inhabit different worlds, how can we compare them? How can we claim one is objectively better? If assessment is only possible within a paradigm, then agreement within the scientific community becomes the ultimate arbiter, undermining the idea of a single, objective method, O.C. Sun, and cumulative progress, O.C. Qi. Incommensurability has two main flavors. Semantic incommensurability focuses on meaning. Kuhn and Feyerabend pointed out that the meanings of key scientific terms change drastically across paradigm shifts. Mass in Newtonian physics versus relativity space, and time in Newton versus Einstein. These aren't the same concepts. There's no neutral language to translate between them perfectly. This leads directly to relativism. If languages or theories are truly incommensurable, how can we compare their truth claims? Davison famously challenged this, arguing that for something to count as a language, it must be translatable, making semantic incommensurability impossible. Kuhn and Feyerabend likely meant only partial translation failures. Epistemic incommensurability, meanwhile, focuses on reasoning and rationality. Different paradigms, or even different cultures, might operate with different styles of reasoning, different standards of what counts as rational. Feyerabend embraced this, arguing we should respect these differences, which directly challenges the idea of a single universal scientific method. O.C. Sun. So, relativism about science is a potent idea. It forces us to question the assumptions we often take for granted about objectivity and universality. However, many philosophers and scientists remain unconvinced by its more extreme claims. Why? Because, despite the critiques, science demonstrably works incredibly well. It allows us to explain phenomena, make predictions, and manipulate the world with astonishing precision. And this success seems remarkably consistent, regardless of the cultural background or gender of the practitioners. This practical effectiveness of science provides a strong counter-argument to the more radical forms of relativism that seem to undermine its very possibility. For those interested in diving deeper into these complex debates, the provided references offer a wealth of material covering various aspects of realism, relativism, and the ongoing discussions in the philosophy of science.